All right, welcome everybody. Next week we're going to start using a culvert analysis and design software package called HY8. I talked about this in the prior class. It's automatically installed with WMS, but if you're using a different machine than you were when you installed WMS, you can obtain it just by doing a Google search for HY8, and it'll automatically be the first result. You can download it directly from the Army Corps. And homework 11, which is the last WMS assignment you've got, which is related to doing a stochastic analysis of a certain watershed. I think it's the Four-Pole Creek watershed that goes by the park. That assignment's due on Monday, and then on the 8th, class is going to be online because I already mentioned this to the hydraulics section. Some of you are in that, but for those of you who aren't, the eclipse is that day, and I plan to be up in the eclipse zone. So if you want to do that, I think it's a great idea. I've seen one before. It's pretty interesting to be there. So we'll just have a recorded class lecture for that day, Monday the 8th. So we're going to move on from watershed modeling and get into some hydraulic structures. The next part of this class is going to be more design oriented. You know, till now we've been doing a lot of underlying science, analysis, and now it's going to be when you know the flow rate that's going to be coming out of a watershed, what sorts of things can you do to size the pipes and the bridges and the channels downstream. So if you want to follow along in the book, this is in chapter 16 of your textbook. Does anybody have any questions before we start talking about flumes today? Okay, so, it's not the Army Corps, it's Federal Highways that makes HY8. But if you just do a Google search, then you'll find it pretty quickly. Okay, a broad-crested weir is one way of determining the flow through an open channel. And basically what a broad-crested weir is just a step in the bottom of the channel that's high enough that forces critical flow over the obstruction. And if you're confident that the step is high enough to force the critical flow, then that allows you to determine the flow rate through the channel by measuring the depth of the flow, and then remember the little kind of shortcut that the specific energy when the flow conditions are critical is 3/2 times the critical depth. And then if you know that the specific energy can be defined, excuse me, and that allows you to classify the flow rate. So basically, broad-crested weirs are a way of identifying what the flow through a channel is. And you may think that that would be a straightforward thing, but unlike in a pipe where we can put in like a magnetometer-based flow rate measurement, it's a little bit more difficult to necessarily know how much water is going through an open channel. And so broad-crested weirs are one way that have been used in the past to determine what the flow rate is, but there's a big disadvantage with a broad-crested weir, and that is the accumulation of sediment and debris on the upstream face of that step. So they work by forcing critical flow, but the disadvantage is that energy is lost and that operationally they require some maintenance to ensure that your weir doesn't become clogged and that that debris isn't accumulating. And so a number of years ago, about 100 years ago, what they realized was there was another way to measure flow, to measure the flow rate in an open channel, but that could avoid that disadvantage. And that's with a flume. And in contrast to a weir, which is a contraction in the form of a step up where the flow is encountering a step that has to flow up over, and it's forcing the critical flow over the obstruction. In contrast to that, a flume has a contraction where the channel is becoming narrower, but the flow isn't having to go up over an obstacle. And so by making the channel narrower, it's causing the same thing, a restriction that's forcing certain flow conditions where you're able to classify the flow rate on the basis of the ratio of depths on two locations inside of the flume. There are these calibrated empirical equations that we'll take a look at in a minute. But it avoids the sediment deposition because actually, as the water's going through the contraction, the velocity generally increases, and so there's no possibility of sediment settling down. It's not that the water is going slower through the contraction, it's actually going faster through the contraction. And so just from the standpoint of maintenance, they're a lot less work. So let's take a look at a flume video here. Oh, we should be watching this because we all get to concealed carry starting in January on campus, right? So this is a very opportune commercial. Oh, let me stop this. So that video mentions two of the primary advantage of a Parshall flume, one being that there's a wide range of flow rates that they can be sensitive to, and that the calculations are relatively easy as well. Prior methods of quantifying the flow rate that had flumes that didn't have the the downward slope in the throat, they required more than just two measurements. And now typically in a Parshall flume, you're just measuring the flow depth at two locations, and then the empirical equations, which are calibrated to tell you the flow rate, are just based on those two depths. So here you can kind of see a side view of what a Parshall flume looks like. Here's a top view, and the main components that you need to be aware of is that in the converging section, the fluid is accelerating. And that acceleration continues in the throat, where the throat has a pretty steep downward slope to it that forces critical flow conditions. And then in the diverging section, the flow is decelerating again, the channel width is increasing. And so what they're measuring is the depth of the water in the throat and in the converging section to try and know whether there is a submerged hydraulic jump or whether hydraulic jump is not submerged. So here you can see in the cross-sectional view that this steeply sloped throat section is what forces critical conditions because the slope is enough that water gains some energy as it's going down there, and then there are ratios that you measure the ratio of the upstream depth and the downstream depth to know whether the hydraulic jump is submerged. There's a correction factor that has to be applied if the hydraulic jump is submerged. And if it's not, you just use this equation directly, but if the hydraulic jump is submerged, then you'd subtract out some flow to account for the inefficiency of having the submerged hydraulic jump. So these equations, you can kind of get a sense for, in some cases, how simple they are. For a throat width of less than a foot, then the flow rate is just based on this upstream water depth. And what they'll usually do is have a tube connected to a section inside the converging section. Sometimes they'll have like markings on the side of the channel, and then they just measure the depth that way. But sometimes if there's ripples in the flow, it can be a little bit harder to get an accurate measurement of the depth. And so instead of doing that, sometimes they'll have a connecting well and then a tube that's outside of the flume that you can use with like graduated markings on the side of the tube to measure the depth of the flow at those two locations. So up to a width of about a foot is just the upstream depth that the flow rate's dependent on. Beyond that, then there are these increasingly complicated exponential functions that we have to be even more careful about. The the possibility of submergence because of the effect that it can have on the flow rate. So the process of calculating the flow rate in a Parshall flume is to first look at the ratio of the throat depth of flow to the upstream flow in the converging section, and these are criteria beyond which the hydraulic jump is considered as submerged. And that's where a correction factor has to be applied. But if the depth is less than these limits, then no correction factor is required. And if you do have to apply a correction factor, what you do is you first find the base free flow Q value, and then you would go to a figure like this, which is given for a certain throat width. And we have a variety of equations depending on what the throat width is. And sometimes these nomographs are available for the exact throat width that you've got. Other times you have to kind of extrapolate to the throat width that you're working with. You'll notice, for example, this throat width of 30 centimeters all the way up to 2.4 meters. That's a really wide range of flume size that applies there. And if you only have the correction table for a throat width of 0.3, but you have an actual flume throat width that's different from that, then we have a way of kind of applying and extrapolating to the actual flow conditions that we've got with this correction factor. So we're going to go through an example where we, from start to end, do the analysis of looking at the two depths to try and assess whether the hydraulic jump is submerged, calculating the free flow rate, and then applying a correction flow rate based on the correction factor and what we read off of the nomograph. So for that example, we're going to work with a flume that has a throat width of 0.61 meters. And what we're talking about here, if we go back to the view here, 0.61 is this width. The narrowest section of the flume is called the throat. So in this example, the throat width that we're dealing with is 0.61 meters. And from the problem statement, what we're told is the depth in the converging section is 0.45 centimeters, and the depth in the throat is 0.39 centimeters. So the converging section, H sub A is 0.39 meters, and H sub B, the depth of flow in the throat, is 0.39 meters. So the ratio of the two, H sub B to H sub A, is 0.39 divided by 0.45, so 0.867. And for the flume that we're working with, our throat width is 0.61 meters. It puts us in this range where the maximum allowable H sub B to H sub A is 0.7. So this is greater than 0.7. So therefore, the throat is submerged. That just means that the water isn't flowing through the flume as freely as it would if the depth wasn't quite so high. So this is showing an example of a submerged hydraulic jump. If the water level wasn't so high at B, then you could actually see the hydraulic jump going through its accelerating phase, getting supercritical conditions, going through a hydraulic jump in the expanding section. But H sub B is too deep, and so you're not actually getting as much water through the flume as is predicted by our empirical equation. So the empirical equation for a throat width of 0.6, the equation that we're using is Q is 0.372 times the width of the throat, then times 3.281 H sub A, and that's to the power of 1.570 times W, and then W is to the power of 0.026. So we've got an exponent to an exponent, basically, in this empirical equation. And like, how are these equations developed? Well, it's certainly not a fundamental equation, which is like derived from the basics of science. This is just a empirically observed. They did a lot of tests in a lab to find out what's the flow rate and what factors does the flow rate depend on. And there's just the depth upstream and the width of the throat that dictates the flow rate through this flume. And so you can buy commercially available flumes from like sometimes places that sell like preformed concrete structures, like you can buy concrete manholes, concrete pipes. They'll sometimes make concrete flumes like this. There are also plastic ones that are portable and can be moved from agricultural field to agricultural field, just set down right in a ditch, and then the water flows around through the flume in order to quantify the flow rate. When you get one of those commercially available flumes, typically the manufacturer would also specify what the capacity equation is for that. So in our case, what we know is the H sub A is given as 0.39 and the width is 0.61. So if we just make those substitutions into the equation, then we can start to get a sense for what the free flow capacity would be. So 0.372 times the throat width of 0.61 meters to the power, times 3.281 times the upstream depth of 0.39 meters. And then that's to the power of 1.570 times the width, 0.61, to the power of 0.026. All right, let me pause for a moment, and I want to see if, given a complicated equation like this, if we can all get the same thing. What would be the free flow capacity of this flume? And then we're going to have to correct the free flow capacity because it's submerged. But substitute the values into this formula. Let's see if we get what the Q value is for that. Excuse me. Okay, so just to kind of recap, we checked the submergence. It's above the allowable limit, so we know that we're going to have to do a correction after calculating the free flow rate. And so for the H sub A value being 0.45 meters, then the free flow capacity is 0.4151 cubic meters per second. Did anybody else get that as well? Only two people? No, I saw some nodding heads. All right, so we have broad agreement that that's right. Okay, now that's what it would be if it wasn't submerged, but it is, and so now we have to go through the step of finding out what is delta Q. Delta Q consists of two things: the correction, and then if we're using a figure that applies to a different width than we have, a correction factor. And that is going to be the case. If you look at this figure that we're using, applies to a throat width of 0.3 meters, but our throat width is 0.61. So how do you use this figure if it's for the wrong throat width? It's just by scaling it up with the correction factor. And so our correction factor, let me just erase some of this so we've got more space. Okay, so the correction factor that'll apply for us is 1.8, because we're using this figure which is based on 0.3 meter throat width. If you've got a throat width that's 0.61 meters wide, then it's just 1.8 times as much correction that's going to need to be applied. So 1.8 is the correction factor. Now, for the delta Q, what we do is we look at the percent submergence that we've got. And just to remind you, our percent submergence was 86.7. That was the ratio of the depths. 86.7% submergence. And so on this figure, what we'll do is look for the intersection of the upper head height and then the percent submergence curve. And so our upper head, H sub A, was 0.45. So on this figure, basically, I'm going to draw a line going sideways from 0.45. And this is a logarithmic scale, by the way. So if you look, for example, 0.3 isn't halfway between 0.2 and 0.4. It's offset. It's a little bit closer to 0.4. So if I'm looking for 0.45, that's going to be about here. So I'm going to have, maybe I need to make that a little bit more visible. So I've got that line at an H sub A of 0.45, and it's going sideways, and I want to intersect the curve for 86.7%. So I'm just basically looking for 87%. So it intersects, it's hard to do, 86 and 88. So 87 would be between those two curves, and then I want to go down from there. So let me draw another line from that point of intersection. So let's just see. I need to maybe move that a little bit further to the side. No, I've got that on the 88 to 90. So I need to move that. Let's see. Here's the 86 curve. Here's the 88. Okay, so it's between the two and going down. Right. So when I previously have looked at, like, where does that intersect with the horizontal axis, I've said that looks like 0.044 cubic meters per second as the correction. You know, if this is, once again, not a linear scale, it would make things a lot easier if it was a linear scale, but it's not. So, you know, 0.05 would be about here. So we're not quite halfway between 0.04 and 0.05. So that's why I said 0.044. So the correction is 0.044 cubic meters per second. And now delta Q is the product of the two. It's 0.044 cubic meters per second multiplied by 1.8. And so the delta Q is 0.0792 cubic meters per second. And then the corrected flow rate, like the Q actual, is the free flow capacity of 0.4151 cubic meters per second minus the delta Q, 0.0792 cubic meters per second. So 0.3359.
Where does the correction factor 1.8 come from?
Well, what it comes from is if you have this figure, which applies only to a throat width of 0.3, in our problem, we have a flume with a throat width of more than double that. The throat width of our flume is 0.61. And so what they've done is they've looked at how much correction needs to be applied to larger flumes than the one that you have a figure for. And so this is just a ratio of how much the correction should be based on using the throat width of 0.3 as the figure. So this is just a given table. It comes from our text, and I think they've done comparisons of different throat widths and how much the correction factor varies between them. So this is showing that what we did was we found the free flow capacity, then we found out how much correction needs to be applied based on the percent submergence and the upstream depth, H sub A. That's how we got the correction, and then the delta Q is the correction multiplied by correction factor, and then the overall non-free flow capacity is less than the free flow capacity would be, by about 25%. That's how much water is restricted by having the hydraulic chump submerged in the way that it is. So it's surprisingly accurate, despite what feels like maybe you're jumping through some pretty odd hoops and using a really strange empirical correction factor. These Parshall flumes have they stand the test of time. And so it's an important way of being able to measure the flow of water through a channel under a really wide range of conditions. That you could use the same flume for a pretty low flow rate during the drought months of the summer and a pretty high flow rate during runoff in the spring. The same flume can be accurate over a wide range of flow rates. The next hydraulic structure that we're going to be talking about is culverts. And on Monday we're going to start to do some design and analysis using HY8, but today we'll just talk about the purpose and some of the typical characteristics of culverts. Broadly speaking, they're used to pass water under a road at a location where it doesn't make sense to put a bridge. If you've got less water going through a channel and you don't necessarily need the complexity and cost of a bridge, sometimes it's just easy enough to put a pipe and put the bridge or the road, put the road or driveway or whatever you need over the pipe. It could be as simple as a concrete pipe that maybe has some concrete wing walls on it. Sometimes it can be a corrugated metal pipe. Those are typically used for culverts because of their low cost, and they're relatively corrosion resistant. Despite being made out of metal, the galvanization usually lasts in a service life of 50 years or even longer. So they're considered a pretty inexpensive way compared to the alternative, which is building a bridge. How much water you're able to get through a culvert depends on a lot of interrelated factors. The biggest of them is the diameter of the pipe. And obviously you're not going to be able to pass sufficient water through a culvert if you've got a really small pipe diameter. But it's not just the diameter that dictates how much water can go through a culvert, because the length of the culvert can have an effect depending on whether the culvert is inlet controlled or not. The slope of the culvert sometimes can be a dictating factor in how much it's able to carry. And then you can sometimes affect the flow rate capacity of the culvert depending on whether you have just an extended pipe coming out without kind of the mitering that's shown here, or if you have an approach channel that guides the flow and tries to reduce the energy lost as the water is going into the pipe. That can sometimes enhance the capacity of a culvert. And then also the conditions on the discharge end of the culvert. When the water exits the culvert, if you have a really narrow channel or a channel that's really shallow, sometimes the tailwater can affect the capacity of the culvert if the downstream end of the culvert is submerged in water itself. So the software that we're going to use, HY8, takes all of these things into account and really simplifies what previously was a pretty complicated process of, first of all, analyzing what was the controlling factor, whether it was the inlet, whether it was the slope of the culvert or the roughness of the culvert. Previously, before the analytical software became widespread, it was kind of a cumbersome thing to design a culvert and find out what the flow capacity is. Here are some pretty interesting photos that come from different places in West Virginia. This is the Bluestone River in Mercer County, and you can see this is just a temporary structure that's put in place during construction. The disadvantage of something like this is obviously the accumulation of debris upstream of the culvert, and so if they leave all of those branches in place, then this is basically going to become a dam. And then water is going to go over the top of the culvert. And flow over the top of the culvert is a very interesting name. It's called overtopping. If you've got flow going over the top of the culvert, it's easy to remember. But it can be a problem because if water's going over the top of the roadway surface, then it can cause a lot of scour on the roadway, and obviously people can't drive over the road if the culvert is completely submerged and the water spilling over the road. Then it makes it unsafe for motorists to go over the top. So we typically don't see multi-barrel culverts like this for the long term because of the excessive amount of maintenance that's required. Here's another look at it. Here are some culverts that I've seen on several occasions. This is in Leadville, Colorado, and this is the headwater of the Green River up in the mountains of Colorado. And this is a little bit different because this is a mountain stream that is really affected by the temperature of the air, because the snow melt speed depends on whether it's cold conditions or warm conditions, and so it's somewhat less affected by the rainfall, but it's, how much water is going through these culverts depends a lot on how snowy it was during the previous winter, and then what's the temperature at any given time and how much the snow is melting. So it's interesting just from day to day, even if it hasn't been raining, if you've got a really warm day for several days in a row, then the flow rates can be higher at this particular location. They've got just the water plunges over the side and discharges into the stream downstream of the culverts. And so this is a case where the tailwater conditions could affect the flow potentially, except for that the stream is so much lower that usually the channel downstream isn't going to be in contact with the water that's in the pipe unless there's some sort of an obstruction in the channel downstream, like debris or something. Sometimes culverts are just as simple as a series of concrete boxes that are connected. So this is almost approaching like bridge type category again. So maybe it's a hybrid in a sense, except for that what would make this more of a culvert than a bridge is that the concrete extends to the bottom, so it's concrete all around. And so you can see that these wing walls, the purpose there is to prevent water from scouring the soil that's supposed to be supporting the road that approaches the culvert, and also to guide the flow and try and reduce the amount of energy that's lost as it's approaching those barrels. Each one of these is called a barrel in the terminology of culverts. And so this would be like a 4-barrel culvert. This is a 3-barrel culvert. Sometimes the culvert would have a natural channel underneath where they just kind of build over it, but then they leave the original natural materials underneath. You can see that over time, depending on the flow conditions, that the water can do quite a lot of damage to the bed, and also there can be scour and damage to the side of the culvert that affects the flow capacity. And so sometimes you have to go and do an inspection, even if the design said it was supposed to have a uniform bed that was laid out on a certain slope, and maybe it's supposed to all be concrete. Over years of the concrete getting broken due to differential sediment, or broken due to vandalism, or broken due to bed load and rocks moving over it, and then the concrete washes away. Sometimes the actual conditions in the field no longer match what's specified on the drawing, so you sometimes have to go and do an inspection and get a sense for how do things really look today in order to model it correctly and know what the flow capacity would be through the culvert. Here's another look at just a corrugated metal pipe. And one of the things that's interesting about these corrugated metal pipes is that they develop some of their strength from being crushed and beginning to go from spherical shape to being deformed slightly. And let me show you what I mean by that. The corrugations provide quite a lot of strength, and it's not as flexible as it would be if it was uncorrugated. But with enough load, what happens is that a circular pipe, you'd want to pack quite a lot of soil under the haunches of that pipe, because when a heavy load is applied, what happens is that it begins to be a little bit deformed this way, and it compresses the soil that was underneath in that area, and as the soil compresses, obviously it's going to be pushing back. And so they kind of depend on or recognize and accept the fact that the pipe's no longer going to be perfectly spherical. As you begin to load it, it's going to deform slightly, but you want to have like a compactable material on the underside of the pipe in order to allow it to have, like, you wouldn't want to just have a single point of contact. If it was just like completely rigid, then it wouldn't be able to develop as much strength as if the soil underneath is all well graded and compacted and kind of resisting the downward force with upward force on the underside of the culvert. So it's just a conduit that conveys flow under roads, and they're used because they're cheaper than bridges, easier to construct, faster to put in place, easier to maintain in a lot of cases. You know, even though you sometimes have to move debris out of the way, it's cheaper than doing bridge inspections and repainting and all of the maintenance associated with bridges. And so the sizing can be a complicated analytical process where you would find out what is the flow rate that you want to pass, or how regularly you want the culvert to fail. Like, do you want the culvert to only fail once every 25 years? So meaning, if you know what the 4% annual exceedance probability is for a certain flow rate, then you'd pick how regularly you want the water to go over the top of the road and size the culvert according to the flow rate that's related to that return period. And I think we'll just leave it there for today. We'll get into some of these features when we talk about HY8 next week. So please be sure that you've got that installed before class on Monday. And then the other thing to remind you about is homework 11 is due on Monday before class. So I will see you then.